All right, this is section 8.2. This is a continuation of functions. This is going to specifically concentrate on linear functions and see what those are all about. So let's take a look at what a linear function is looking like. So linear, what does linear mean? Linear means that graphically it's going to form a line. Okay, so they look like this. All right. And the typical linear function looks like this, mx plus b. Now, take a look at, like for instance here, it says ax plus b. They're going to just flip the letters around and that doesn't mean anything. So m here, a there, who cares, okay? So in any case, the number that sits in front of the x, which is your variable, because this is telling you that it's your variable. So this is a constant here, m, is your slope, and the b is the y-intercept. So if we specifically have a line, okay, the y-intercept is the spot that it crosses the y-axis. Okay, so that's this point right here. And interestingly enough, no matter where it crosses, even if I'd have a line up in here, and this is your y-intercept, your x-coordinate of that is always going to be 0. I'm always going left and right, nothing, and just going up and down. So at your y-intercept, it's 0 something. Okay, that's a very important piece right there. We're going to need that. And the slope is the pitch, the rise over run, rise over run, rise over run. And the thing about a line is it has a slope. Other functions such as quadratics, parabolas, rationals, things like that, they don't have a slope. So it's specific to lines. All right? So let's go back to my math lab here, and first of all, let's see whether or not symbolically something is a line or not. What we're looking for is the form mx plus b. Now this one sort of is that form. We've got 7 plus 5x. Now we can always rewrite that. Okay, so I could always rewrite that into f of x equals 5x plus 7. I'm going to keep my 7 positive. I'm going to keep my 5 positive. I'm just going to rearrange them. Okay, it's more in that form. So here we can see that the 5 is the slope. The y-intercept is at 0, 7. Okay. What we're looking for on our variable x here is that, number one, it has a power of 1 on it, so there's no power on there, but you guys know that if there is no power, it's really a 1 on there. So this means it's a linear, it means it's a line, the power on x. And there's nothing else going on with this x. There's not a square root over it, there's not absolute value bars, cubes, and, you know, anything goofy going on with it either. It's not in the denominator, it's just a plain old x. So this fits the linear model right here pretty well. So we're going to say that yes, it is a linear function. A here is the same as m in mine, so we're looking for the number that sits in front of the variable x, whether it's messed up like this or rewritten down in here like that. So a here is a positive 5, all right, and b is this number right here, the one that sits without the x, that's the 7. Okay, so simple enough. Let's see here. Let me get this down just a bit so that we can see it. There we go. All right, so now we're going to decide whether or not this is linear. Remember I said that on x it has to be a power of 1. This has a power of 2. So this function is definitely not linear. Okay. We've got a square root over this one, so that's not linear. Now this one's missing the mx piece of it. But I can always rewrite this. Let's try to rewrite that. So let's say I have f of x equals 0x plus 5. Can I rewrite it? And is that the same as f of x equals 5? Because 0 times anything is 0. And 0 plus 5 is 5. So really this is another way of writing this. So those are identical, and this is in the mx plus b form. So this is linear. It's definitely a linear function. It's a very specific type of linear function though. Okay? M, when I write it this way, remember m is the one that sits in front of the x, is going to be a 0 in here. And b is the 5. Let's take a look at what that thing looks like graphically. What this is saying is f of x is equal to 5. Y is equal to 5. No matter where I go on my line, y has to be stuck at 5. So that means it's a horizontal line. All right, let's try this. Let's clear this out of here and just do 5. See that horizontal line? All these points here, and you can look at your table even, no matter what x is, y is stuck at 5. So it forms a horizontal line. It's called a constant function. It's also a linear function. It's both. Okay, constant means that it's running this way. Now if I had an x equals 2, that's going to be a vertical line running through here, x equals 2. Okay? So we do have, you know, some that are a little different than others, but they're still linear. Nothing to worry about there. This is also linear. We can rewrite this one as f of x is equal to negative 3x plus 0, right? It still fits that form, so it's definitely linear. All right. Okay, so let's take a look at just visually. This is down as it gets. Okay, visually, seeing if something represents a line, it's super easy. We're just going to be looking for a solid line, either horizontal, vertical, or at an angle. This is definitely not a line. This is a line that's been broken in half. So this is not a linear function. All right. That is not either. Boy, those are really... Okay, so let's just get over here and let's just put one in. Let's do 5x plus 2 plus 6, let's just say. There's a linear function, forms a line, okay? So those are not linear. All right, so this is probably the hardest one to decide on. So visually, graphically, we just look at the picture and we see if it's a line. Symbolically, we're looking at the power on x. Now this is the numeric representation, which is a little tougher, okay? So the thing that I said down here was specific to linear functions is that it has a slope, okay? If it's not linear, it's not going to have a slope. So let's get the definition of what slope is. All right, so we know that slope is the pitch, okay? It's also rise over run for those that have worked in carpentry or anything like that. Okay, mathematically, this is a Greek letter. It's not a triangle. It's a Greek letter called delta. All right, so this is delta, and what it means is change in. Okay, so we have delta y over delta x. So the change in the y, so up and down, divided by the change in x, left and right. If we wanted to put this into a formula, which we'll use later, we'll use this. For right now, we're going to do change in y over change in x. Okay? So keep that in mind, that that's my slope. So let's go back up here to this table and start calculating these out. So we're going to take any, remember f of x is y, we're going to take any pair. I'm going to go from this point to this point, just randomly. Okay? My change in y is 10 minus 0 is 10. Okay, so maybe we should be writing this down here. Let's see if I can't. Can I move that down just a bit? There we go. All right, so my change in y is 10 minus 0. Okay, that's change means difference. Difference means subtract. So I'm going from 10 to 0, and now I'm going to go from the same points in the same direction, but just my x values, 3 and a 1. So that's going to go down here. So I have 3 minus 1. Okay, that's my change in x. So 10 minus 0 is 10. 3 minus 1 is 2. 10 divided by 2 is 5. So far between those 2 points I have a slope of 5. Well, the thing about a slope is it never changes from point to point because the line is the same everywhere. So the slope is the same everywhere. So that means that if I would go from another set of points, let's just say this one to this one, okay, just randomly I'm going to pick this one and this one, it's got to have the exact same slope. And if it's not, then it's not linear. If it is the same, then it's going to be linear. Or it's going to be very close to being linear. We have to check all points, but we're going to check another one. So we're going to go from this one to this one. All right, so we're going to go back down here. We're going to do the change in y, change in x. We said that we're going to go from 5 to a negative 5. Be careful here. We're subtracting a negative, which is like adding. And then we're going to go up to the x values, 2 minus 0. So 5 minus a negative 5 is like 5 plus 5, which is 10 over 2, which is 5. Okay, let's just do one more just to prove to ourselves that these are the same. Let's just go between these two. Okay, so one more just to see if it indeed is a 5 down in here. So I'm going to do change in y over change in x. We have 10 minus 5 over 3 minus 2. 10 minus 5 is 5. 3 over 2 minus 2 is 1. 5 divided by 1 is 5. So yeah, it's linear. It's got the same slope no matter what two pairs of points I pick. I calculate the difference between them. Okay, that's the change in. And I calculate out the slope. I see that it's all the same. So indeed, this is definitely linear. Now I have to write my equation. Okay, I've already got my slope, my m, right? Now we're doing the mx plus b instead of the ax plus b up here. So I know my slope is 5, so I'm going to put the slope in. I know this is my variable, so that never changes. This is going to be a plus, okay? We'll leave that alone for right now. And let's look at the b. The b was the, let's go back up here. The b was the y-intercept. What did I say about the y-intercept? I said that it's always 0 something. Remember, this is an ordered pair here. Okay, so, oh, what did I just do? Darn it. Full screen. No! Okay, I'll be right back. I gotta fix this. Okay, I'm back. Sorry. I don't know what the heck I hit. I'm gonna make mistakes here, just to warn ya. What was I talking about? Okay, I was talking about the y-intercept. It's always got 0 something. I was talking about this being an ordered pair. Better not do it again. X and y. So x is 0 always, and y is just some number. So let's go back to our table and see if we can't pick that off. Well, of these points, x is 0 here, and a corresponding y value is negative 5. So it would be plus a negative 5. Plus a negative 5 is the same as subtracting a 5. So we're going to subtract a 5 here. Okay, so we've calculated out our slope down in here, okay, to be 5. X is our variable, and then we have to pick off our y-intercept, and that's going to be wherever x is equal to 0. And then we're going to check our answer. Excellent. Okay? So you've got another one to do here. We're going to check to see if it's linear or not. We've got the y-intercept sitting right here. So really all you have to do is calculate out the slope. First of all, see if it has a constant slope, and if it does, then that will be your m. All right? Okay, so this is the same one. I'm not sure why they just all of a sudden didn't have the boxes around it, but this is the same thing here. Okay, so let's take a look at this one, and let's try to find out if this one's linear or not. So let's just take this point, just randomly, and this point, okay? So, all right, so we have delta y over delta x. So we're going to go from -4 down to 2. And up on top on the x values, we have 2 minus a -1. All right, so -4 minus 2 is -6. And 2 minus a -1 is like 2 plus 1, which is 3. And -6 divided by 3 is -2. So I've got a slope of -2 between this point and this point. So let's just go between this point and this point. Again, I'm just picking random things just to try a few. Okay, so now I have -3 minus 2. Okay, so that's this point and this point, I think I said. And then I'm going to go from here to here. 0 minus a -1. So -3 minus 2 is -5. And 0 minus a -1 is like 0 plus 1. And -5 divided by 1 is -5. These are different numbers. Therefore, it can't be linear. So it's got a different slope running through two different points. So graphically, this thing would be like, you know, like that. Because each piece in between each set of points has a different slope. That's definitely not a straight line. Okay, linear means straight line. It can't be like crooked in any way or whatever. So this one's not linear. So as soon as you find two that don't match, excuse me, then it's not linear. Now, there might be two that are the same. Like, let's just say you pick a pair and you pick another pair and it happens to have the same slope. You got to be really careful because it could have the same slope between a few points, but that doesn't necessarily mean it's linear. It's, you know, it could have it between a few points but not others. So you have to make sure you check more than just one set. Okay? All right. All right, so we're in question number 11 here. Well, this one's interesting, isn't it? Look at the y values. They're stuck at -4. What is that? That's like, isn't that like this one here? F of x is equal to 5. All the y values were stuck at 5. Here they're stuck at -4. Okay, so this is a horizontal line running through -4, just like this one was. The x values can all change, but the y values cannot. So therefore, this is a constant function. It's a linear function. Okay, so this one's definitely linear. So we're here, and f of x is equal to -4. That's, you know, we've got a 0x, we've got a slope of 0, and we've got the y-intercept at -4, and this is definitely linear. Okay? All right, so numbers 12 through 16, we're going to give you some more practice at evaluating functions. This is just like 8.1, so I'm not going to go through these. You're evaluating this function at this point, and then you're evaluating it again at this point. Okay? And again. And here you are evaluating off of the graph, just like before. These are all just stuck at linear, though. 8.1 had some different ones in there. Here's a constant function. And going to be sketching a graph. Okay, so this is again review. Well, I don't know if we did one like this. This is f of x is equal to 1. This is one of those constant functions. So let's just pull this down, get our graphing tool palette down here. All right, so we want to get a line. Y is equal to 1. Okay, so just pick a point. 0, 1. Pick another point. 7, 1. Okay? So it's a horizontal line where the y values are all stuck at 1. There is no x in this equation here, or this function. Okay, so we can graph. Just be careful on this one. MyMathLab will not allow you to go in between grid points. So for instance, I can't pick x to be 1 because then y would be 1/2. And it's not going to allow me to do that. So I have to pick points that are integers. Okay, so here I would want to pick 2 for x because half of 2 is 1. Or I'd pick 4, 6, 8, things like that because I can take them in half. Okay? And then this one's also a graphing. All right, so we're getting close here. All right, let's look at the midpoint. The midpoint of a line is the halfway point. Okay, so it's right about there, maybe there. Okay, so we have a formula that I'm going to write down for you because some of these won't be so easy. And the midpoint, now this kind of stuff you're going to want in your notes, like this. You know, that the slope is the change in y over change in x, that kind of stuff. So the midpoint formula is another one that you want to, you know, get some sort of a notebook with, you know, formulas and that kind of stuff, just so it's really easy to find. But the midpoint formula goes like this: x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2, comma. No comma, sorry. So this is your x coordinate and this is your y coordinate. So really all we're doing is we're averaging, because this is really an average. Okay, so let's look at what we got up here. What is this point here? Well, we are over, there were -1, 2, 3, so we got -4, -3. Okay, so we have -4, -3. That's one point. The other point that we've been given is 2, 3. Okay, so what I'm going to do is I'm going to randomly call this point number 1 and point 2. I could have done it the other way too, it doesn't matter. In that case, this is x1, y1. Okay, these are subscripts. That means it's the x-y combination in regards to point 1, and then this will be x2, y2. Okay, so what I'm doing is I'm just labeling things. So y1 is -3, x2 is 2, like that. And now I'm going to put them into this formula so I can keep everything straight. So x1 is -4 plus x2 is 2 divided by 2. y1 is -3 plus y2, which is 3 over 2. And now I'm going to simplify these. I've got a -4 plus 2 is -2. And -2 divided by -2 divided by 2 is -1. Here I've got a 0. 0 divided by anything is 0. So I'm guessing that this is the midpoint. I'm not guessing. I should never say that. We don't guess in this class. We calculate. All right, so -1, 0 is right about there. Does it, first of all, look like a reasonable answer? Yes, it certainly does. Okay, so type an ordered pair. Now I could go to my keyboard and do a parenthesis and a comma and all that kind of stuff, but I can also just use this and fill in the boxes. Your choice. So I've got a -1 and then I just tab over 0 and we'll check to see. Excellent. Okay, so you've got a few of those in here. You know, you've got some points that you've been given. You could say this is point 1 and point 2 or vice versa. Doesn't matter. You're going to have some negatives in there. You might have some decimals in there. They're all done the same. Okay? So let's move forward and do a few word problems. 23 through 28 here are all application problems. And since this is your first set of application problems, I think I'll run through them with you so that you know, you feel comfortable with them. Most people really, really hate word problems. I'm not sure why. I think they're wonderful because it shows you why the math is useful, why it's needed, you know, real life application things. So, but I'm biased probably. Okay, so read through this. We've got a particular charge card. Ooh, boy, that's a big charge card. 164 billion. I guess it was the government's. In 1993 and 243 billion in 1995, and we want to estimate the debt in 1994. Well, 1994 happens to be right between 93 and 95, so it happens to be the midpoint between the two that we know. So what we can do is we can form two different points off of those and calculate out the midpoint. So I'm going to say point 1 is 164, 1993. Okay, so this is my debt. This is my year. I could have gone the other way. Didn't really matter. And my other one is 242 in 1995. Okay, so here's my x1, y1. Here's my x2, y2. And I'm going to use my midpoint formula. I'm going to average out my debt. Then I'm going to average out my year. And I can go over here and try to use my calculator if I feel like it. Pretty easy stuff. If you're not going to put parentheses around that, you're going to have to hit enter first and then divide by 2. Otherwise, we can use parentheses. I'll do parentheses on the next one. And then the second one, if we use parentheses, we're going to contain them 1993 plus 1995 and parentheses. I want to take that whole thing divided by 2, and I get 1994, which is a good thing because that's what we're looking for is 1994. 1994. So if my x-coordinate represents my debt and my y-coordinate represents my year, then I've got $203 billion in debt in 1994. Okay, and since my math lab here comes in so many billion, I don't want to put in all the zeros. I just want to put the 203 in there. Okay, let's take a look at another one. Boy, we are spending a lot of money. Same thing here, okay? I'm not going to do this one. $84 billion in 91, $116 billion in 95, and we want to know how much we've spent in 93. 93 again is halfway between 91 and 95. So you can set up your points, 84, 1991, 116, 1995, and make sure that your y-coordinate comes out to be 93, and then you'll see how much you spent. Okay? All right, so we've got a function. It's describing the temperature of a room that is kept at 72 degrees for so many hours. Okay, what does that look like? That to me looks like a constant function, right? The y value is not changing. Okay, so x hours, hour 1 at 72 degrees, hour 2 at 72 degrees, hour 3 at 72 degrees. It never changes. X changes, the hours change, but my y value never changes. So here's an example of a constant function that really works. So here's my domain. I'm going to look at a 24-hour period, okay, and I want to write a symbolic and a graphic representation for this function that I'm keeping it at 72 degrees for so many hours. So symbolically is the first one. Okay, let me drag this down so that we have a little bit more room to look at it. We don't have a slope. Well, we do, it's 0, but we don't have the mx piece of it. Okay, so y is stuck at 72, that's our temperature. Okay. And now I'm going to select the graph below. Well, I know that it's a horizontal line. I know that the y value is at 72, so what I'm going to do is I'm first of all eliminating this one and this one, because both, look at these two. They're both tipped. They both have a slope. They both have an m associated with them, so it can't be those two. We know that when y is equal to 72, we've got a horizontal line. So now we're just looking at the scale here. Okay, we've got 50, 60, 70, 80, something, no, 50, 60, 72 degrees. That one looks about right. Constant function. So we'll choose that one. Now we're going to complete the table below. Okay, remember, x is the hours, y is the temperature. Hour 0, hour 4, hour 8. Okay, what are all my y values? Well, we're not moving the thermostat. The thermostat is staying at 72 degrees for a period of 24 hours. We're not moving it. Okay? So no matter what hour, if you're between these x values, the temperature stays constant. Therefore, it is a constant function. A constant function is linear. So it's not a nonlinear function, but it's constant and linear. Excellent. Okay? Let's see. Okay, let's read through this one. We've got a car that's initially 20 miles south of the border between two states and is traveling south. Distance d, okay, that's this whole value here, which is like your y values because it's underneath, between the car and the border are recorded as the hours move forward. So when you're sitting still and you're just taking off, you're 20 miles south. 2 hours later, you're 100 miles south. 3 hours later, you're 140 miles south, okay, of the border. So we're supposed to write a function, okay, d of t. Now we've got, instead of an x, we've got a t. So that means time is the variable right there, which is this. So what we're doing is we're looking at a function that as t changes, okay, d changes. So this is a function in time. Time and distance are related by this model. Okay? So we're supposed to, whenever we're supposed to model something, we're supposed to write a function of this data that's modeling the function. What we're doing is we're taking a look at what's going on within this table, and we're going to try to write a function for that. And again, if it's linear, all we need is m and b. In this case, we need a and b. Okay, so let's figure out what the slope is. We're going to take any 2 points. I'm just going to pick these two, just because I can. Okay? I'm going to go down here. I'm going to calculate out my slope. I've got delta y over delta x. Come on. Delta x. I've got 220 minus 140. I've got 5 minus 3. I must be pushing on something here. There we go. Sorry about that. Okay. 220 minus 140 is 80. Five minus 3. Boy, I should be able to do that without a calculator. Should be able to do this without a calculator. So we've got 40. That's my slope. So far, I've got 40, and I better be careful. T. Okay, now my math lab wants this variable to match that variable, so don't put an x in there. If you put an x in there, it's going to say it's wrong. It's not really wrong. It's just my math lab says it's wrong. Okay? Now remember, we're going back to the y-intercept. The y-intercept is where x is equal to 0. X is t. Y is d of t. So here we have The x coordinate is 0 when the mileage is 20. Okay, so that would be plus 20. Excellent. Okay, so we've written a function according to the data that we've been given. Now we can figure out at any given hour how far away we are, right? I could put in, let's just say that I was, driving this car steady. I mean, this is assuming that I'm driving this car steady at the same speed forever. Okay, so if I put in, t is equal to 200 hours later, I can figure out where I am. Okay, obviously that's not true real life, but, well, you know what I mean. All right, let's look at this one. All right, so we've got some gas. It's heated. It expands. We've got V of t. Okay, so let's break this down. T, capital T, is the temperature in Celsius, and V of t is the volume. So the temperature and the volume are connected. So as the temperature increases, what happens to the volume? It increases, right? It says right here, when it's heated, it expands. Okay, so they're connected through this function. So we're supposed to evaluate V of 0 and interpret the results. Well, this is just like when we were evaluating f of x, right? If I would say, if this was f of x equals 0.165 x plus 35, and I wanted you to evaluate f of 0, what you're doing is you're replacing the 0 with the x. Well, here you're replacing the 0 with the t. It's just a different letter. So I put a 0 in here, and I crunch the number. Well, anything multiplied by 0 is 0, so 0 plus 35 is 35. So we're just going to put a 35 in there. I hope that is okay. And then we're going to interpret. The value of V of 0 means that when the temperature of the gas is, okay, remember we said that this was the temperature and this was the volume. We have to remember what side we're on. We put in a 0 in here. So when the temperature is 0, the volume is 35 cubic inches. Okay? If the temperature is increased by 10 degrees, how much does the volume increase? Be careful with this question. I mean, take a look at how it's asking you for. It doesn't want the temperature, or excuse me, it doesn't want the volume, it wants the volume increase. Okay? So let's put in 10 here and crunch out to see what the volume would be. Okay? It increases by 10, so we've got 0.165 times 10 plus 35. It goes up to 36.65. Okay? It was at 35. So we're going to have to take the difference between those. Certainly don't need a calculator for that. Okay, the volume increases the difference between those two. It's not the volume that it wants the volume increase. Okay? What is the volume when the temperature is this? Well, now it's asking you for the volume, the actual volume. So we're going to put in this is actually asking you for V of 100. We'll put 100 in right here. And then it's asking us for the true volume. So we'll try it again, 0.165 times 100. It's 35. So it's 51.5. Okay, it wants the decimal in there. Good job. Okay, so be careful with that about this is asking you for the volume and this is asking you for the volume increase from the original 35. All right, last one. Okay, we have a custom t-shirt shop. Let's talk about fixed costs and variable costs. Okay, so the fixed cost means that no matter if you make 0 t-shirts or 2,000 million, 2,000 million. If you make a ton of t-shirts, you've still got that $300 cost. Okay, so it's probably, for using the machine and, making the logo and, blah, blah, blah. The variable cost is $4 a shirt, and it varies on how many shirts you have. So if you have one shirt, it costs $4. If you have two shirts, it's $8. If you have three shirts, it's $12, but you always have that $300. So we want to write an equation so that we can say, we can figure out what the cost is no matter how many shirts she makes. Okay? Now this is a linear equation. We have the mx plus b format. So we have the variable cost of $4 a shirt. We have x shirts, so that's your slope, 4x. Okay, so this is your variable that goes with the x. And then we always have to add on $300, right? So if she makes 0 shirts, it's $300. 4 times 0 is 0. 0 plus 300 is 300. She still has to pay that. If she makes one shirt, 4 times 1 is 4, plus 300, she's got a $304 bill. And so on and so on. Okay? So now the cost of producing 5 shirts is really like evaluating C of 5. So we're putting a 5 in here. So 4 times 5 is 20. And 20 plus 300 is $320. So that's her cost. Okay? I think that's it for the section. So you have, I hope, enough ammunition here to get you going on your homework, and I will see you for 8.3.